Now our topic is the magnetic dipole moment. Actually, what I have said here about the similarity of the magnetic field of a loop of current or a ring of current and a real magnet, which we call a magnetic dipole, by the way, well, tells us that a loop of current in this case behaves like a magnetic dipole, okay? And so we call it a magnetic dipole. And we define a quantity which is called the magnetic dipole moment of that loop of current. So any loop of current behaves like a magnetic dipole, and we can define the magnetic dipole moment of this current, of this loop. The magnetic dipole moment of a loop is defined as, it's a vector. It's given by the product of the current flowing through it, which is a scalar, multiplied by an area vector. Now we are used to the idea not of area vectors, okay, from Gauss law, you remember. How do we define this area vector? This area vector is defined again by a right-hand rule. What's this right-hand rule? In the loop, you let your right-hand fingers point in the direction of flow of the current, okay? You have a loop, there is a current flowing, you let your right-hand fingers flow in that direction. Your thumb will give you the direction of the area vector in this case, which is the same as the direction of the magnetic dipole moment, okay? So mu vector is equal current multiplied by area vector in this case. Now, the SI units in this case are, as you can see, it is just, ampere meter square. This is amperes, this is meter square, okay? So that's what, these are the units of the dipole moment. It doesn't have a name by itself. For a current loop, for example, the magnitude of the dipole, in this case, the dipole moment, magnetic dipole moment, is, take the modulus of this. So the modulus of this is equal I multiplied by the modulus of the area. The modulus of the area is just pi r square, so mu is equal I pi r square, okay? So this is the magnitude of the dipole moment, magnetic dipole moment of a circular loop of current. But this definition applies to any loop, not only to a ring. This is the special case when you have a ring. This definition applies to any loop, so don't misunderstand me. I said when you have a loop does not mean a ring only, okay? So this is something that you define for any loop, okay? Planar loop. So if you have any loop of any arbitrary shape, defines a plane, find the direction of the right normal to it by using the right-hand rule, okay? Then the dipole moment, the magnetic dipole moment, is just I multiplied by that area vector. That area vector, it has magnitude equal to area, and it's given a given direction, okay? And it's given by that rule. For the special case when this is when the loop is a circle, it's a ring, in this case the area is pi r square and I, so this is the magnitude. What's the direction? For example, in the example given, shown in the figure, the current is flowing this direction, so the dipole moment, the area vector, and so the dipole moment is upwards, So the magnetic dipole moment, as you can see, is pointing in this direction, okay? This is becomes important because, as we will see just in later videos, that when you put a dipole moment, a magnetic dipole moment, in a magnetic field, then it will feel force in this case, okay? And more precisely, it will feel a torque, and it will start rotating. Just as when we put an electric dipole in an electric field, it starts rotating or dancing in that field. Here also, when you put a magnetic dipole moment in a magnetic field, then it will feel a torque and it will start dancing also in that magnetic field. So this is why it's important to understand how you define the direction and the magnitude of the magnetic moment of any loop. So here the direction is upwards, and this is the magnetism. P pi r square, the area of the enclosed by the loop. Okay. Now we can express the magnetic field of the current loop actually in terms of the magnetic dipole. So for example, at large distances, you remember, when you are away at large distances from along the axis of a loop, at large distance, we found that the magnetic field in this case was given by this expression. Okay? And you can express this if you just multiply. This is IA square. Multiply up and down by pi, you get I pi a square, which is just what? Which is just the area. So I multiplied by pi a square is just the magnetic moment. So you can express Bx as mu naught mu over 2 pi x cube. Okay? So mu now is the magnetic moment. So B field is actually, if the loop is proportional in this case to the magnetic moment of that loop. So this expression looks like I have a looks like the magnetic field of a dipole, which goes like, you know, p over x cube. It goes like, drops like p over x cube. So when you have a ring of charge and look at it from a large distance, the magnetic field there at the axis is just equal to mu over, is proportional to mu over x cube. Okay, so it increases with the mu and drops at 1 over x cube. So you can express it that way.